pairs of all the charges that are there. So this is the main three ones we're talking about. All of these have been zero pointed. In this lecture, we're talking about a different quantity called potential. We call it the electric potential V. Okay? Not to be confused with the potential energy U. I don't know why they did this. Terrible naming convention. U, it's energy, units joules. V is a new thing we're introducing today, and it's the final topic of part 1 of the course. So the electric potential is units volts. V is another confusing thing. Typically we use capital V for the variable for potential, but the SI units is also a capital V. So like volt, you can have V equals 20V, but V would be the units. So it's a bit confusing there. But this is also a scalar quantity. Okay, we know energy is a scalar quantity. This new potential we're defining, it's also called, it's also a scalar value, so that's what makes it easier to work with. And basically, we can write down V, the potential, which can represent the electric field because the electric field is what we call a conservative vector field. So because the electric field is a conservative vector field, we can rewrite it in terms of the potential, only because we have that feature of the field. You can do the exact same thing for Newtonian gravity. You can define a potential for gravity as well in this way. Potentials, they're very important in higher level physics. You might have heard of stuff like gauge theory or gauge invariance if you've ever looked into physics before. A lot of that is actually based on writing theories in terms of their potentials. So when we write down these theories in, like for gravitation and electromagnetism, often we work in terms of potentials, not fields, when we're defining these things at a fundamental level. So potentials are very important in our foundations of physics. We're going to spend all of today on it. So how is it defined? The electric potential difference, so negative delta V, is equal to the integral of the electric field dot product with the infinitesimal displacement vector. For example, on the x-axis, that would just be Ex dx. Now, what we do, and you might notice this is very similar to the relationship between potential energy and force. It's like the identical integral. So potential energy and force have the same relationship as potential and field here. This delta V is what we call the potential difference. This is something very similar to potential energy. For potential energy, it was delta U that physically mattered, right? Because delta U is how we define work. Similarly, it's delta V that physically matters. We're going to have to zero point for this stuff too. So if you're in a circuits lab, for example, and you measure, there's potential, this is the potential we often talk about when we talk about circuit theory. When you measure the potential across a circuit element, you're finding this delta V quantity, okay? So if we want to find an isolated expression for just V, we have to pick some point and set it equal to 0. As a rule of thumb, the places we zero pointed for potential energy are the same ones we're going to zero point for potentials. So for point charges, we'll zero point at infinity, and for capacitors, we'll zero point at one of the plates. Right, so let's talk about the zero pointing stuff. Why? Why do we zero point? I want to spend some time this lecture just talking about this kind of generally so you can kind of have a conceptual understanding of why we would do this. So as I said, this delta V is what physically matters. But delta V can be the same thing for different choices of VA and VB. We can have different values for VA and VB and have the same delta V. So let's take a look at some examples here at the bottom of this slide. you can have VB equals 40 and VA equals 10, delta V is 30. You can have VB equals 90 and VA equals 60. Delta V is again 30. You can have 170 and 140. Delta V is again 30. You get the point. You can pick any two values there that have a difference of 30 and end up with the same delta V. That's what we would physically measure. That's what the physics depends on. This is how the electric field is defined in terms of potential. So the feature that we take advantage of with the zero point is that these endpoints are relative values. As long as the relative difference between the two is associated to what we would physically measure, we can pick anything we want for those endpoints. So what we do, if we want to find an expression for just V instead of delta V, we say, okay, one of these ends is going to be 0. The other end will be V. And we're measuring V relative to that one point. So when we say 0 pointing, we're picking a 0 like the ground for gravity. And then anywhere above the ground, when we say the potential energy is mgh, what we were really saying is it's mgh relative to u equals 0 at the ground. We do the same thing with these potentials and potential energy and electrostatics. So essentially, 0 pointing, it's the delta V that's the physically relevant quantity. We want to isolate for V, so we set one of the ends equal to 0. So what we typically do, as I said, typically we'll say, well, VB will just set equal to V. That's the expression we want to find for what is our potential. And VA will set equal to 0. We'll say at this point, potential 0, such that our delta V is just V, whatever that value is relative to 0. So this allows us, instead of always working with this delta, to get an isolated expression for V. We don't have to do this. This is not like something we must do. It's kind of a conventional thing we do to get isolated expressions for potential for different scenarios. Delta V is always defined in general in terms of the integral of the electric field there. So same zero pointing conventions as before. That's what we're going to do for some examples here. What other reason we zero point? Well, remember, we said work, that's the physically measurable quantity, is negative delta U. Well, what we'll see later is that delta U and delta V are related. In fact, delta U is Q times delta V. You might see that already because of how similar the delta V definition was to the delta U definition. They were just the same thing multiplied by Q. So that's where this comes from. The point is, if we plug delta U equals Q delta V in here, we see that work is also defined in terms of the change in potential. So change in potential or change in potential energy, it's this delta that define our work in terms of, not the individual value at some particular point. Okay, let's talk about, I just mentioned there's a relationship between U and V. So what is that relationship? Well, at the start of the lecture, we introduced equation 7 here. Equation 7 states that the negative change in potential equals this integral of the electric field. But last class, we had something almost identical for the work. Work is the negative change in potential energy, which is the integral of force relative to some displacement. So potential is field relative to displacement. Potential energy is force relative to displacement. These definitions are very similar. And how we can relate them is to recognize that this F here, the force, is QE. replace f here with QE, we're left with the integral of QE here, right? So, what do we want to do? Let's take this equation 7 here and multiply both sides by big Q. So we multiply this side by big Q, we get negative Q delta V. This side by big Q is a constant we can pull in here. We get the integral of QE, but that's just force. It's the same integral. So we can just relate those two integrals here by multiplying one by Q, or conversely taking Q out of the other. And what we're left with is that negative Q delta V is equal to the work integral, but so is negative delta U. So we're left with work is the integral of force, which is negative delta U, which is negative Q delta V, which is where that relationship came from on the last slide. So basically delta U equals Q delta V is how we relate potential and potential energy. Essentially, you just multiply the potential difference by Q, you get the potential energy. Let's do an example here of how this stuff works. Let's go back to our parallel plate capacitor. So, this is a good one. And I got rid of those lines that were in the diagram there and just cleaned this up a bit. Inside our capacitor, the electric field is what we call uniform, right? That was a big part of last lecture. We have a uniform electric field inside the capacitor, which means every vector is pointing in the same direction with the same magnitude. Everywhere we look, you can pick any point inside there, the electric field vector is pointing in this direction with the same magnitude. Just like Newtonian gravity did near the Earth's surface, right? So this is very similar to our near Earth surface problem. Here we have a positive point charge at x equals 0 here on the negative plate. Remember, the positive charge is attracted to the negative plate. This is like a ball resting on the ground here on Earth. And we want to ask ourselves how much work, or last class we asked ourselves how much work to lift this thing up to some point x, just like we would lift a ball in the past in high school or last semester. We did that same thing for work. Now we can ask ourselves, let's do that same thing for the potential. It's essentially the same problem we did last class, but what we have to do is do that electric field integral. Well, we know the electric field vector is pointing in the negative x direction here, right? This is our x-axis. This is x equals 0 here. All these electric field vectors are pointing in the negative direction. When we take that charge and we lift it like this, what happens? Well, we have to do the integral of E relative to dl. So dl, what is dl? dl, that's our infinitesimal displacement vector. It's just pointing in the direction we're going. So if we're going in the positive x direction here, this little dl vector is just going to be dx 0, 0, right? It's just going some little bit dx along our x-axis here. So what we're going to do, we're going to have our electric field vector, we have our displacement vector, we just have to take the dot product of those two and then add it all up. So how does this work? Here's all our quantities here. Our electric field, we know it was pointing in the negative x direction. We have negative Ex 0, 0. We have an infinitesimal displacement vector, dx 0, 0. So we end up taking the dot product of those two things. Because we see here in our integral, we have to take the dot product of E and dl. So if we take the dot product of E and dl, well, the y and z components are just 0, so it's a super simple dot product. We have negative Ex times dx, we have negative Ex dx. This is going to be in our integrand there. Well, we also have the 0 point. Remember, at x equals 0 on the left plate, we set the potential equals 0. So we want to integrate to some other point x, and at that point we will find our isolated expression for v. So we just take all this stuff and plug it into our definition. Well, we have a uniform electric field, so E is a constant. Just toss that thing out of your integral, you're just left with the integral of 1. So the integral of 1 dx is just x. You're left with negative e delta x from this process. Now, the important thing to do is to put in our 0 pointing values. So from our integral, we have delta v equals ex delta x. Well, we set v equals 0 at x equals 0, the initial positions. We're left with v equals ex times x for the potential anywhere in our capacitor. Now, if you remember back to last class, we did the same problem for the potential energy. For the potential energy, we got Qex. So potential is Ex, potential energy is Qex. If we sub this one into this one, we get the relationship U equals Q times V, which is the same thing we just got a couple slides ago relating potential difference in potential energy. Why is this important? This is what we found before. This is our general physical relationship. This is true, U equals QV, for our parallel plate capacitor example. Why? The only reason this is true is because we zero pointed at the same point for last class's problem and this one. We set the left plate in our capacitor to have 0 potential. Only when we do this can we relate our 0 pointed expressions. Otherwise, it would be nonsensical. So if you 0 point at the same point for potential energy and for potential, then the expressions are relatable. That's kind of the main point here. We can relate them. This is a general expression. This is always true. Delta U equals Q delta V. But if we 0 point at the same spot, we can do U equals QV. That's going to come up again and again here. Let's do another example. Let's do the point charge example. Point charge example, this is an important one. Basically, this is the same. Again, these examples we're doing right now are identical to what we did last class. Except we're doing field instead of force. Right? Delta U is related to force, delta V is related to field. So we have our electric field due to a point charge at the origin along the x-axis here. So let's do that same delta V calculation where we have to do the integral of our electric field. Well, K and Q are constants, so we can pull it out front. We have the integral of 1 over x squared, just like we had last class. The antiderivative of 1 over x squared is negative 1 over x. So we can quickly do this one. Antiderivative of 1 over x squared is negative 1 over x. But remember, for the point charge problem, we 0 point at infinity. So our initial x, we have here our lower bound of the integral as infinity. And essentially we're asking ourselves, what's the potential difference at some point x relative to infinity? That's the point where we 0 point for these point charge problems. Why did we do that? Well, one of the reasons is that when we evaluate this integral, we're going to have 1 over infinity. That's just 0. We're left with k q over x is the potential due to the point charge. So what is this expression? For a single point charge, the electric field is defined everywhere, right? Now, for that same single point charge, we can define the potential everywhere. But how do we define, this is what the potential is due to that one point charge at the origin. But how do we do that? We say this is the potential of our 1 point charge relative to infinity, right? Because delta V is always what's defined. So this kind of famous KQ over the distance formula for a point charge is just when we 0 point at infinity, we can obtain this thing. So that's our point charge. And this thing actually works more generally. So first off, we had KQ over X for the single point charge. last class, we said, what's U for bringing another point charge in from infinity? That was KQQ over X. So if we relate what we got this class, KQ over X, to last class, KQQ over X, we get the relationship U equals QV again. It happens again. So the point is, we're zero pointing at infinity, whether it be potential or potential energy, because we have the same 0 point for our point charge problem. We still have U equals QV relating potential to potential energy. Now, the reason we did this for X is just to make the math easier. And we were saying, let's do this along the X-axis. Bring the charge in from way at infinity to some point X. This law is valid in 3D. We're not going to do it because it would be a 3D integral, but basically, you get the same thing. The potential for any point charge Q at any other point is KQ over our big R. This is the same big R we had before, which is our physical distance from the point charge to where we want to calculate the potential. So this big R here is our physical distance, and that tells us where we, like let's say this water bottle is our point charge, and let's say we want to find the potential here. Well, what's big R? It's just the distance to that point where we want to find the potential. So it's very similar to what we did with the electric field. In fact, in my opinion, it's a lot easier. This is a scalar. We don't have to worry about unit vectors, or this vector, or that vector. We just got to figure out how far away is the point from the charge. And that's how potential is defined for a point charge here, 0 pointed at infinity. Let's do a really quick other example. It's like the same example, but just to emphasize. If you do something like we did for the charge of sphere. So from Gauss's law, we found that the charge of sphere has the relationship kq over x squared, where q is the total charge of that sphere, if we were finding a field along the x-axis somewhere. This was just the same expression as we had for the point charge. So finding the potential outside of the sphere ends up being mathematically the exact same problem. You end up with the same integral to 0 point at infinity. So for that charged sphere, we would 0 point at infinity, ask ourselves what's the potential outside of the sphere. You just have the identical integral to the point charge problem. And you're left with kq over x for the potential. So charged sphere, point charge, exact same problem. You're just computing this integral here. Okay. Now we get to a really important question. We spent a whole lecture finding the electric field due to a point charge. Then we spent a whole lecture asking ourselves, well, what's the electric field due to multiple point charges? So we could ask ourselves, what's the potential at some point due to multiple point charges? Yeah, no question. Yeah. Okay, good question. Does x include the radius of the sphere? Yes, x for the sphere problem was always relative to the center of the sphere. We were finding the electric field, like in the Gauss's law. The way to think of it, for Gauss's law, if you have a charged sphere, and you place a Gaussian sphere around it, the radius of the Gaussian sphere goes to the center of that inner sphere. Yeah, exactly. Okay, so we can ask ourselves, now we have more than one point charge. How are we going to find the total potential at some point? I've kind of spoiled it here, my bad, on the slide. Superposition. Exact same thing as before. The superposition principle works. If we find the potential due to a charge, 0 pointed at infinity, and we keep adding more charges, the total potential at a point is just the sum of all those contributions. Same as before, this time way easier. no vectors. No vectors. We just gotta write down what V is the scalars and add them up. So here it is. Superposition principle for potentials. We simply add up KQ over R for each one of our charges. Now, R is the magnitude of our big R vector from before. So mathematically, this is basically the same thing but easier than the electric field problem. You just calculate your big R vector like you've been doing over and over, find its magnitude, plug it in, that's the potential for any given point. All right, so let's do an example problem to see how this works. Let's find the total potential V at point 250. So we're going to have two charges. This could just as easily be an electric field problem, what we're doing for potential. We'll have two fun charges, so each of them, KQ is 1. We place the first charge at the point 1250. So we know our R1 prime vector is 1250. We place the second one at 8, -30. So just like always, that means our R2 prime vector is 8, -30. And finally, we have to define point P. That's what our little r vector is. That would be the vector 250. So we have each of the required vectors to define our big R vectors. What do? This is identical to before. You just subtract the vectors to find your big R's. Then you find the magnitudes. Look, I picked some nice numbers in this problem. That the magnitude of both of them is 10 when you work it all out. And now it's a super simple problem. We have to use the superposition principle. What's the superposition principle? Let's look down here at the bottom. We have to sum the contribution from each of our point charges. How many point charges do we have? 2. So we have 1, 2 terms. We know KQ is 1 for both of them. We know R is 10 for both of them. So we have 1 over 10 plus 1 over 10 equals 2 over 10 equals 0.2 volts. Okay, so that's how you can figure out what the total potential is at a point. You just use superposition like before. All you need is the magnitude of big R. You plug it in, you find your total potential. So finding potential as a rule of thumb is easier than finding the electric field. Let's continue this example. Let's add a third charge. Let's add a third charge. But now we're going to say it's a negative 1 charge. So we have just the same thing, values of course only negative, such that K times Q will be -1. And we're going to ask ourselves a bit more of a deeper question here. Where could we place this charge such that the total potential is 0 at our point P? So we have our point P 250. Where do we want to place this new charge to P equals 0? Yeah. Infinity won't be possible. So it's an interesting thought. We can't place it in infinity because at 0 point at infinity, delta V would be 0. It actually won't end up contributing. So we're going to have to place it somewhere. How we do it, we're going to have to use the superposition principle and figure out where that charge has to be essentially. So where could we place it? Well, we know from the superposition principle that the total potential is just the 3 terms now. We have 3 charges. The original 2 plus this new charge. So what do we have to do? We already figured out the total potential to these 2 terms. That was 0.2. So we can replace these 2 terms with 0.2. We know K times Q is -1 for the -1 charge. So we can replace that here. We're left with this expression. For the potential to be V equals 0, at that point where it was 0.2 in the previous problem, the new charge is going to have to perfectly cancel this. right? So the new charge is going to have basically negative 0.2 potential, right? If you had 0.2 there before, you need negative 0.2 there for it to go to 0. So if b equals 0 at our point, and we had 0.2 before, we just have to rearrange for this big R for our new charge. We get the big R is 5. What does this mean? This means that if we place a negative charge anywhere a distance of 5 away from our point P, we will have B equals 0. We will have 0 potential at that point. So essentially, we can place it, it's not just one spot we can place it. We can place it in many points, and lots of those points will make it cancel. I gave some examples here. You could place the new charge at 590, negative 220, 750, 200. All these are just a distance 5 away from our point P. Right? So you can pick literally any point to place this third charge that is a distance 5 away, and it'll perfectly cancel. What would be nice too is you could draw like a grid here. If you plot all these points and draw a circle around point P, all of these points would be on that circle around point P. Okay, so we have a few more topics here to wrap up part 1 of the course. First, I want to talk about the relationship between all these quantities we've talked about. We've talked about electric field, potential, force, potential energy. Let's start with these two, E and B. Potential difference is the integral of the electric field. Think back to mechanics last semester. Velocity was the time derivative of position. But on the flip side, position was the integral of velocity. Right? Those go back and forth. If you take a derivative of something, the integral is like the inverse operation. That is also true for all these quantities we define. So potential difference is the integral of the electric field. Conversely, the electric field is the derivatives of the potential with respect to each of the x, y, and z components. So if you take the negative x derivative of v, negative y derivative, negative z derivative, those are how you can write your field in terms of your potentials, if you know your potential as a function of x, y, and z. So our electric field we know has an x, y, and a z component. Therefore, each of those components of the electric field, like Ex, for example, is just the negative x derivative of v, and so forth. You might wonder, what's with these curly derivative symbols? Okay? We talked earlier about multivariable functions, where something depends on more than one input parameter. The potential depends on x, y, and z. Therefore, the potential is a multivariable function. When we take the derivative of a multivariable function, we need these curly ones, we call them partial derivatives, to specify which one of those inputs are we differentiating with respect to. I'm not going to test you on that on this midterm, but it's going to be important in part 3 of the course when we get to topics that are very heavily involving these partial derivatives, okay? In a nutshell, a partial derivative has the exact same rule as before with your derivatives, except if you're taking the partial derivative with respect to x, you are saying you're treating y and z as constants, and the same for the other ones. So you're just taking the derivative with respect to x, everything else is a constant, you follow your usual derivative rules. For a really quick example here, we found v equals kq over x. According to our rule here, e has to be the negative derivative of v. So if we take the negative derivative of kq over x, we get 1 over x squared times the negative sign from the x derivative. We're left with, because remember k and q are constants, we can pull them out. This is just the derivative of 1 over x. We're left with kq over x squared, the same thing we had before, right? So you can go in both directions with your field and potential. If you know your potential, you can differentiate to find your field. What about those other quantities? F, E, U, and V. Force, electric field, potential, potential energy. These are all related to one another. Here we have force and field, both vector quantities. Here we have potential energy and potential, both scalar quantities. Potential is related to field in the same way potential energy is related to force. Electric field is related to potential in the same way force is related to potential energy. Force and field are related by multiplying Q. Potential energy and potential are related by multiplying Q. You can see there's a lot of symmetry at play here between our fundamental relationships. Okay, there's reasons for this, because it's a conservative field. Because it's a conservative field, we can write down the potential and potential energy scalar values. And they all become related through methods of calculus. If something's a conservative field, there's a theorem in calculus that allows you to write it in terms of some scalar value that we call a potential. We're not going to get into that in this course, but that's why this stuff works out so nicely, is the nature of the electric field itself. So all this stuff is related. Anyway, so a couple more topics here. Electric dipoles, just really briefly introducing this, it's something you should be, I don't know, maybe aware of. Electric dipoles, pretty simple. If you have an equally charged positive and negative charge, a small distance away, you can find the electric field on either axis here relatively simply. A general expression for anywhere on the axis. We define this thing here, this vector P, that's not momentum. This is called the dipole moment vector, pointing from one charge to the other. It allows us to write down some simplified expressions. I'm not going to make you know how to do this. Basically, you do it and you can write the electric field on either axis in terms of that dipole moment vector. So on the y-axis, you could write it as the top equation. On the x-axis, as the bottom equation. So basically, you can express the dipole in terms of that dipole moment vector and figure out what its electric field is. You might wonder, this seems kind of random. Why would we introduce this? Well, dipoles are actually found often in nature. In fact, water molecules behave kind of like this. So it's of interest to people doing kind of biology-related type stuff. Maybe even some chemical engineering applications would be interested. So when we define this dipole moment, this P, we can define things like torque and potential energy much easier than if we had to do this all from scratch. Like we just have two charges here. We could do it all from scratch like we've been doing in this course, or we could work with it as this one object called a dipole moment. The torque is the dipole moment across the field. The potential energy is the negative dot product of the dipole moment of the field. So you can work in what's the torque and potential energy. Because basically what happens, when you place a dipole in a field, I think I have some pictures here. When you place a dipole in a field, one end is positive, let's say the top of my hand. One end is negative, let's say my elbow. So if it's in a field, one end is being forced one way, one is being forced the other way, it's going to get torqued to align with the field. So if you have a bunch of dipoles and you put it in a field, it torques them to align with the field. This is something like with water molecules. If you have a bunch of water you can align them with an electric field such that all the molecules are pointing in the same direction. There's various reasons people want to do this for application, but essentially you can align them. I think this is called polarization in some fields. Basically, you can use an electric field to align a bunch of dipoles for some particular application. It may be more of an interest to the science side of things, but some engineering applications I'm sure would be interested in this as well. Okay, and finally, our last thing I want to touch on in part one of the course. A blast from the past here. This example I hated. And you might be wondering, why would we do this example I don't like? Okay, well, why didn't I like this example? It's because it was so gimmicky, right? We had these trig triangles and stuff. We weren't following rigorous rules of procedure, which makes things more logical and easy to follow. This one we had to say, oh, well, by symmetry, y and z fields are 0. We just have x. Let's add them all up. When we did that earlier in the course, we found the electric field anywhere on the axis was given by this expression here. I wanted to show you what happens if we did the same thing for potentials, just because it's kind of cool. So if we did the same problem for potentials, we have to find some dV, the potential due to that little bit of charge on the ring dq. What is it? Same expression we just introduced. K times the charge dq divided by the distance. Remember, the distance for the ring problem was the square root of x squared plus a squared of the values in that diagram up there. So if we want to find the total potential, we integrate to add it all up. Think back, I'm just going to remind you, when we did this problem before, everything in here, the integrand was a constant. K was a constant, and this distance was a constant. Because if you center a ring on an axis, the distance to the axis from every point on the ring is a constant. So what happens at school here? Well, we basically don't have to integrate. We can pull out the constants. We just have the integral of dq. What happens when you add up all the dq's around the ring? You just get the total charge q. So the integral of dq is just q. We can plug that back in. We have an expression here for the potential. Remember, we found the electric field a few lectures ago for this same problem. Now we have the potential at any point x on the x-axis for this ring aligned on the yz plane. We have also claimed that B and E are related. So let's check it out. We found this before. Now we're saying the potential is this. We claimed that the electric field is always the negative derivative of B. So what do you think is going to happen when we take the negative x derivative of this? What are we probably going to get? The other one, right? The other one. And quite cool, you take this derivative, which is a bit more complicated than the other one we did. Take the negative x derivative, the 1/2 root becomes a 3/2 root, and you get the exact same electric field we got a few classes ago. Okay? So this example is going to conclude our science in part 1. See you Friday. Take advantage of the review stuff, and good luck, everyone. See you then.